Hi guys, we'll give it a minute. How you guys doing this morning? Here it's kind of, I can hear the wind outside. It seems really windy, and I hear it's kind of cold out too. Hope you guys are doing okay. All right. So today what we get to do is we get to finish up chapter 2.6. So we left off with example 8 last time. And we're going to start chapter 2.7, which is a very exciting chapter. And let's see, we can just go ahead and finish up this. Don't forget, today we have a quiz today that's going to open up at noon. Okay, this is chapter 2.3, 2.4. Okay, we also have a test coming up. I believe our test is in a couple weeks, so keep that in the back of your mind. I'll start to, it's definitely getting colder, yeah. That's what I thought too. We have a test coming up in the next couple of weeks, so kind of start keeping that in the back of your mind. I don't think we have any more quizzes after today's quiz, so that all that extra stuff that we're covering from these quizzes onwards is going to be on our test. So our test will just be chapter 2. Okay, so keep that in mind. That's coming down the pipeline, and then I'll start posting practice problems for the test, in the next week or so. I'll put that up where our test is going to be. Let's see, I can't think of anything else. Don't forget our problem set is coming due too, and that's our problem set number 2. There's some chance for extra credit on there as well. And then don't forget, if you guys haven't submitted it already, I need your project proposals. That's just, a non-binding proposal about who you might want to work with, if anyone. And then maybe what you might like to cover in your project proposal. I need you to start thinking about it so that it doesn't come up and crash on you, because we're looking at, we have 1 month left to the semester, and November we have a big holiday in Thanksgiving. So we basically have on that Thanksgiving week, I'm looking at the calendar right now, Thanksgiving week we have class on that Monday, and then we basically are off for the rest of the week. So we almost have a whole week off in Thanksgiving. So keep that in mind. And then the semester wraps up very quickly after that. So we're kind of coming into our home stretch here. So let's give it a good final push. So don't forget, quiz today starts at noon. And then we have a test coming up in a couple weeks. Okay, and a problem set due. And homeworks. We have homeworks due today too, and classworks. Okay, all sorts of fun things coming due. All right, you guys, so let's do a quick review for example 8, and then think about what we're going to be doing for the last part. So we've got the parallelogram, which results when the unit square is transformed by b. So remember, our unit square has one of its vertices at the origin, and it goes 1 unit. It's like our basis vectors, right? I go 1, 0, 0, 1, and then I'm going to basically connect the dots to do a 1 unit square after that. So I've got 0, 0, 1, 0, 1, 1, and 0, 1 as my coordinates for the vertices of my my unit square. This is our transformation matrix, okay, right? And I take this transformation matrix and I apply it to each corner, each vertex on my square, and I get new coordinates, which gives me 0, 0, 2, 3, minus 2, 1, 0, 4. And I'm basically looking at what do I have here? What do I have here for stuff? So if you can kind of think about what's happening, right? I've got a vector here, kind of like a vector here, and I've gone out 2, minus 2, 1. That kind of gives me my column vector here. And I have, if I do this, I'm going to go, that gives me 2, 3. So here's 2 and 3. So if I think about this as a vector right here, I've gone over 2 and then up 3. So you can kind of think about this column vector as representing, this is vector 1, this is vector 2, right, in terms of what we have. So these column vectors represent, right, basically vectors on our transformed unit square, okay? So they gave me coordinates here. Now we want to go back. We want to do a couple things. So we want to find the area of this new parallelogram, right? So I can take the determinant, absolute value of my determinant, right? And it's going to give me minus 6 minus 2, take the absolute value, I get 8. I take the absolute value because my area is always going to be a positive number, right? So the determinant is useful for telling me what's the area of my parallelogram, okay, of my shape. Now I can use this, okay, this transformation matrix, and I can use this to find the inverse matrix. The inverse matrix will take me back to my original shape. So my inverse is 1 over the determinant. Remember, we switched the A and the B, and we negated the C and the B. We switched the A and the D, and we negated the C and the B terms. We multiply that by 1 over our determinant, and that gives us our inverse matrix. This inverse matrix, this last part that we're going to do, is going to bring us back to its original unit square. So I'm going to do that part now. So bringing us back to our original unit square means taking this inverse matrix and multiplying it by each of our vertices. So we're going to multiply our inverse matrix with each vertex of our transformed parallelogram to get back to our original unit square. Okay, so watch what we're going to do, right? I'm going to say my coordinates for my transformed are here, right? We figured these out. So this is 0, 0, 2, 3, minus 2, 1, 0, 4. So I figured those out there, right? So I'm going to multiply this matrix here by each of those pieces. So what I'm going to do is this. I'm going to go minus 3, 8, 1, 8, 1, 4, 1, 4. Then I'm going to multiply it by all of our different pieces. So I'm going to go 0, 0. This is my first matrix, right? So I multiply first row by first column and I get a 0. Second row by first column and I get a 0. So I'm going to go, I'll start keeping a note. So this is going to be 0, 0 goes back to 0, 0, which is what we expected. That's what happened at the beginning. All right, next one, minus 3, 8, 1, 8, 1, 4, 1, 4. I'm going to multiply that by 2, 3, and then see what happens, right? So this is going to be minus 3 eighths times 2, 3 8 times 2, plus 1 4th times 3. This is going to be 1/8 times 2, plus 1 4th times 3. And that's going to give us, so this is going to be minus 6/8 plus 3/8. Oops, sorry. Let's do that like this. So this is going to be minus 6 over 8 plus, this is 3 over 4. I wanted to have an 8 so I can do something with it. So I need to double both. 6 over 8. Oh, look at that. Minus 6 over 8 plus 6 over 8 gives me a 0. This is 2 over 8 plus, this is 3 over 4. I can simplify this to be 1 over 4 plus 3 over 4 gives me 4 over 4, which is equal to 1. So 2, 3 goes to 0, 1. Okay, see how I'm multiplying or transformed? Which look, remember how we did that? I multiplied 0, 1 by that, and it gave me 2, 3. So that kind of makes sense. So far it's working like we expect. I'm going to do the next one. Minus 3 eighths, 1 8, 1 4th, 1 4th. And I'm going to multiply that by my next point, which is going to be minus 2, 1. Okay, so that's going to be minus 3 8 times a minus 2 plus 1 4th times 1. 1/8 times a minus 2 plus 1 4th times 1. Okay, so let's do this. So this is going to be 6 over 8 plus 2 over 8 becomes 8 over 8, which is 1. This is minus 2 over 8, so this is minus 1 4th plus 1 4th gives me a 0. So then that means at this point here, minus 2, 1 goes back to 1, 0. Okay, and our last piece, let's space here. So our last piece minus 3/8, 1/8, 1/4, 1/4. And I'm going to multiply that by my next bit, which was 0.4. Okay, so this one minus 3/8 times 0 plus 1/4 times 4 is a 1. Minus 1/8 times 0 plus 1/4 times 4 is a 1. Okay, so basically our last point was 0.4 transforms back into 1, 1. This is just a summary. I summarized it. So we're back to our unit square. Okay, all I did was prove. I knew it was going to happen because I know that this is the inverse matrix to the original transform matrix, but this is just showing you, right, that I start off with a shape, I transform it with a matrix. If I can find the inverse, right, if I can find the inverse to that transformation, I can go back to where I started from. Okay, by multiplying all of my coordinate points back, get back to my original coordinate points. That summarizes chapter 2.6. I'll give you guys a second to finish writing that out. Before we move on to the really exciting chapter 2.7, then what I'll do is I'll scan in this later today so that you guys can have it. I didn't scan it in before because I wanted to finish up this last problem here. You guys all have that okay? Okay. I'll scan that in and give that to you guys later. All right, so 2.7, I've broken up into multiple parts. Part 1. Make sure I have my lecture examples for 2.7, part 1. I'm also broken up into 2 parts. We're going to talk about why in just a second. 2.7 is really neat because it kind of, like most of our end chapters, going to bring some stuff together, but let's talk about it. Chapter 2.7, I'll call this part 1. And then chapter 2.7 is, the whole chapter is rotations in 3 dimensions. Okay, but we break this up into 2 different parts. I'm going to give you a background idea on like what's going on when we rotate in 3 dimensions. And then we're going to get into the part 1. So we have 2 different methods for rotating in 3 dimensions. Part 1 deals with one method, part 2 deals with another method. Part 1, I start with part 1 first because it seems like a really complicated method, but it actually is computationally less expensive than the method that we talk about in part 2. But I show you both so you have an idea about what's going on. So let's talk about rotations in 3 dimensions, right? So when we talk about rotations in 3 dimensions, let's think about sort of generically speaking, let's do this. I want to be able to, I'm going to draw a picture. This is a very poor drawing of an airplane. Bear with me here. This is an airplane, and I've got wings. Okay, well, let me get my airplane. It's not going to fly. All right. So with an airplane, right? So we have our airplane here. Now we've got, let's say we've got this center point that we're thinking about. We're going to orient to this center particular point here. Now I've got different axes that I can do. So let's do our different axes. So let's think about my airplane. Here's an axis this way, right? So my airplane's sort of lengthwise on the axis, right? If I do like a rotation around this axis here, this is like my airplane is like spinning in space this way, right? This is called a roll. Okay. Now, if I've got, I'm going to try to draw these out. Let's see. Can I draw this out in, it's hard drawing these in, all right, let's draw straight down this way. So if, if I do a roll, I'm rotating like, you know, like the nose still points forward and then the airplane just kind of flips over itself this way. If I do what we call a yaw, okay, what happens is our axis goes this way. So if our airplane is here, then it's spinning this way in space, right? So the roll was just like a log roll, right? It's hard to visualize this. But if I'm doing a yaw, I'm going head to tail this way, right? Okay, so that's my yaw. Now you can imagine I'm going to try to draw so that the yaw goes straight down. And then I'm going to draw this out here. This is at right angles. This is called a pitch. And it goes like this. Okay, the pitch is basically like it goes this way, right? So we've got a log roll, it's just rolling this way. I've got one where it's spinning in place this way, and then I've got one where it's going head over tail. Okay, so I've got these 3 dimensions, right, that I'm talking about. So this is like 1 dimension here, 1 dimension here, 1 dimension there, okay? So we have basically three degrees of freedom, okay? And what's called, I'll write this down, Euler Angles. It looks like Euler, right? But he was a Swiss mathematician. Euler was his name. We're going to talk about him again in chapter 3. But it's pronounced Euler, even though it's spelled Euler, but it's pronounced Euler. Okay, so basically what happens is, so we have a rotation in 3 dimensions. We've got these basically these different axes that I have to think about, right? I'm going to draw it out this way here. I've got my X and my Y and my Z axes, right? And then you can imagine I've got like the negative aspect of these angles that are happening too. So when I go to rotate around my X axis, I've got an angle that's related to my X axis. Okay, now you want to put your thumb on the axis, the positive direction of the axis, and you're doing it with your right hand. You put your thumb on the positive direction of the axis, right? You can see I'm putting my thumb here, and then I'm gonna loop the direction of my hand looped over, tells me the direction of the spin. Okay, this is the direction of positive rotation. Okay, same thing with the Y. I put my thumb on the Y axis, and then essentially I'm rotating this way. This is an angle that I'm forming with the Y axis, theta sub Y. Okay, now with my Z axis, right, I put my thumb on the positive Z axis, and then my right hand tells me the direction of positive spin. Okay, this is our theta sub Z, right? So these are our Euler angles, theta sub X, theta sub Y, theta sub Z. These are the angles that we're forming with each axis. So when I rotate in 3 dimensions, right, with the airplane, you can imagine if the airplane's doing something, right, in space, it's forming an angle with each particular axis that we're working with, okay? So we have to take into account all these different axes that we're working with. Yeah. I can try. All right. So basically, right, if you want to think about, we're going to do one thing. Like if I take a step back, I'm kind of giving you background work before we get into the actual nitty-gritty details of our rotation. So these Euler angles, right, if I just rotate around one axis and not the other 2, they're rotating around only one axis and not the other 2, our rotation matrix looks like this. Looks like this. Okay, so if I rotate around just the X axis, my rotation matrix looks like this. I rotate around the X and not around the Y or the Z. But then cosine of theta minus the sine of theta, sine of theta, cosine of theta. So this is like, I'll draw it out off to the side. It goes like this, just around that axis. So theta then becomes only the angle that we're rotating. Like I'm only going 30 degrees around the x-axis. This is my rotation matrix. Remember, in 3 dimensions, I have x, y, and z components. So I have my rotation matrix has to take into account 3 dimensions. Okay. So when we expand from 2-dimensional rotations to 3-dimensional rotations, Things get much more complex because I've got a whole bunch of things that are happening all at once. Okay, so rotation around the x-axis. If we just go around y-axis, right, by a certain theta angle, we'll draw out the picture in a minute. Sin of theta, 0. Sine of theta, 0. I'm giving these to you so you can see the level of complexity. I'm not going to test you on this stuff. The type of stuff I'm going to test you on in chapter 2.7 is going to be a little more straightforward, but it's helpful for you to know how to visualize. Oops, I drew that as a y. This is a z. Sorry. Okay, so now what's happening is, right, we're going a certain angle theta over just the y-axis. Okay, and this is our rotation matrix. If we're only going around the y-axis, not any of the other ones. These are a little bit arbitrary, like not arbitrary, but they're it's a little bit artificial. Like it's very rare that you're just going to go around, you know, one axis in place, right? It's more likely that the shape that you're working with, you can imagine as you're throwing a ball, like in your game, you're going to throw a ball, it's going to rotate around some spot, but it's the ball itself is going to be, you know, moving. Okay, so if we rotate around the z-axis, what does that look like? Our rotation matrix is going to look like this. Cosine of theta. And then it looks like we're only going around the z. And like that. Okay, and that's a certain theta. Okay. What happens is, right, I mean, like, it's rare that we're only going to be going around one, right? So, I'll give you guys a minute to finish writing that. Okay. The reality is we're mostly doing a combination of rotating around one axis and the other one, right? So I've got all these different angles that I'm forming with each axis, right? So this rotation matrix is nice because it's simple. I'm only dealing with one axis, right? But if I have to take into account a rotation around all three axes, right? Okay, so I'm going to rotate in 3D space, and I'm gonna have a component. I'm going to have a rotation bit around the x-axis, a rotation bit around the y, and a rotation around the z-axis. That means that my total rotation matrix is going to be a product of, I'm going to go around the x-axis by some angle x. I'm going to go around the y-axis by some angle y. I'm going to go around the z-axis by some angle z. So it's a product of all three rotation matrices around each axis, right? So the order here is x, y, then z, but it can be any order. I can go z, y, x. I can go, you know, x, z, y. You get the idea. Like it's arbitrary. The order is arbitrary, right? Because we're going to encompass them all eventually anyway. We're going to multiply it all together, and it's going to be one matrix, right? So essentially, what that's going to look like is, oops, sorry, right? We're going to be looking like, let's see if I can draw this out. You can imagine, let's see. So I've got this thing in space, you know, comes off of my axis, you know, it's doing something, and I'm going to be rotating. It's like it looks like it's two-dimensional, but it's really coming out of the page a little bit. And I'm going to be rotating around this thing, right, by some angle, okay? This theta is going to have components that are related to the x, to the y, and the z. So theta degrees or radians around some object in 3D space, right? Theta is broken into an X component, a Y component, and a Z component, right? It gets really complicated. This is why we start, I'm giving you the background so that you'll see when we do something that looks complex, but it's actually much more simple than trying to break down my theta into an X. Now, I'm going around this red thing by 30 degrees, but what fraction of that 30 degrees is around the x-axis, what fraction is around the z, and what fraction relates to the y-axis. Okay, so you would say angle theta about some arbitrary axis, right? That's our red line. It basically forms an arbitrary axis. And we're going to do these things are linear, containing origin. If we did an affine, we would have that affine translation where we'd move our origin up and come down. So we're just going to talk about linear, containing the origin. And okay, so this thing we're going to say has a unit length that we're dealing with, right? So then U has an X component, a Y component, and a Z component, right? So then basically a rotation matrix breaks down into, I can say, a rotation around U by some angle theta is equal to the identity matrix plus sine of theta times matrix S. We're going to talk about that in a minute, plus the 1 minus the cosine of theta times S squared, where S is equal to, and I'll give it to you here, this is actually part 2, 0 minus U of Z of Y. Okay, I'll write this down. This is our part 2 discussion, right, that we're going to cover in more detail, and this is computationally expensive. Then the stuff that we're going to talk about and method. Okay, so this is preview of coming attractions we're going to talk about, just so that you have the comparison and that you know. This is problem number 1. Okay. Problem number 1 with this method. Okay. Problem number 2 is the angles can actually cancel each other out. Problem number 2 is this. We can get into what's called Gimbal Lock. In game terminology, it's called a Gimbal Lock situation, where one angle about one axis, about an axis, whether it's an X or a Y or a Z, will actually cancel out an angle about another axis. And it's like a mathematical fluke. It's an accident. It's really like an artifact of the math. It's not really happening, but this results in a loss of degree of freedom, right? And it's also kind of like an artifact of using this method. It's not even really real, but it comes out in the math. It's a problem in the math. Okay, so normally, let's write out. So normally, right? We've got, like, let's draw our little airplane again. Oh, there's a little airplane. Right, we've got our, let me draw our circles here. So I'll draw them in different colors. So I've got my direction where I can go in this direction. I've got go my rotation in this direction. Okay, I'll draw it. All right, I can go rotating in this direction. I can go rotating in that direction, and I can go rotating in this direction. Right, we've got our pitch, yaw, and roll. So let's see. This is our roll. Around the top is pitch. And the purple one here is our yaw. Okay, so I'm just trying to draw it out for you. So normally we've got a case like that. Now what can happen is our gimbal lock, right, where the dimensions cancel each other out, are going to look like this. So I'll draw my airplane this way with my wings here. I know I'm not a great artist. My pitch is in red. Right, so I'm rotating around some axis, but then my yaw and my roll line up like this. Like that. And yeah, see how we've lost a degree of freedom, right? So normally, as the airplane is like doing something, it's rotating, whatever, it's got like all these 3 different axes that it's working with, okay? But here, when we're doing something, we've got some kind of what we call a gimbal lock, where the yaw and the roll now combine into one, right? They cancel each other out, so I've lost that degree of freedom that I would have had to normally describe my 3-dimensional motion. And I'm just dealing with pitch, and the yaw and the roll are equivalent to each other, okay? So we've lost that degree of freedom. So that's a problem number 2 with our using Euler's angles to do rotations in 3 dimensions. Problem number 1 is it's expensive computationally. We want things that are cheap computationally so we can do a lot of them very rapidly. Okay. So this is like a background information for why we're going to deal with part 1, our method in part 1. I'll let you guys finish drawing that. Then we'll talk about what is our method for part 1. Okay, you guys all set with that? Okay, so let's get into the details of our part 1. Method of 3D rotation. And we're going to use what's called quaternions. It's a funny name, right? Quaternions. Quat meaning 4. Okay, we have 4 dimensions that we're talking about. So this is a number system that basically it comes from our imaginary number system and it extends our imaginary number system. Okay, so think of your quaternions as basically a combination of, I've got a scalar portion plus a vector. My vector is in 3D and my scalar is just a number, right? So basically what I have is, I'll call this A plus, I'll call this B, right? And this is my quaternion. Okay, A is our scalar, B, C, D is our vector. I can also write this as A plus B times I, C times J, D times K. Remember, I, J, and K are our unit basis vectors. Right? We're dealing with 3D, which is why we have our K there, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so it kind of gives us this. So I can also write this as A, B, C, okay, where this is our scalar portion and these three make up our vector components. Okay, so think about it like that. Okay, so let's talk about quaternion multiplication and how we think about multiplying I, J, and K and how that extends our, complex numbers. So I'm going to think about it's based on this. Okay, so if I've got my X value, and I could have 1, I, J, and K. So remember our unit basis vectors. So I, J, and K are, here's X, here's Y, here's Z, here's 1 unit, 1 unit, 1 unit. This is I, this is J, and this is K. Okay. So I've got this here, I've got 1. And we're going to fill in our multiplication. So if I multiply these together, so if I multiply 1 times 1, I get 1. 1 times I get I. 1 times J, 1 times K. Okay. If I multiply I times 1, I get I. If I multiply I times I, I'm going to get a minus 1. If I multiply I times J, I'm going to get my other unit vector. If I multiply I times K, I'm going to get the other unit vector. It'll be minus J times 1, J times I, minus K. J times J gives me minus 1. J times K gives me an I. K. K times I is a J. K times J is a minus I and minus 1. So I squared equals minus 1. J squared equals minus 1. K squared equals minus 1. Kind of like our complex numbers. Okay. And this is also I, J, K is also equal to a minus 1. Okay, so we're extending our idea of complex numbers, and we're using our unit basis vectors to help us figure it out. Those with the details, I'm trying to give you more background information probably than you need, but how we're going to use it in rotations is going to be the meat of it. Okay, but I just wanted you to have it. So let's talk about why rotations using quaternions are good. Okay, Euler's angles are part 2. I'm going to give you that information. We kind of touched on it just a few minutes ago. But let's talk about why we'd want to do that. Why? Because 1, rotations using quaternions avoids Gimbal Lock. Right? We're not going to lose that degree of freedom, right? The quaternions are going to handle it for us so we don't lose the Gimbal Lock. The other one is the computations. While it seems complex, there's a lot of little things to take care of and to think about. There's actually quite a nice bit of rules that we can follow that are very consistent, and the computations themselves are faster, meaning they're cheaper on our computer, and they're more compact than matrices. Okay, we're just dealing basically with, you're going to find out, we're dealing with vector multiplication, dot products and cross products. So it's basically just multiplication and addition, as opposed to matrices where I've got to keep track of all these, complex arrays. And then essentially we only have 1 degree of freedom that we have to worry about, right? So I've got this three-dimensional shape. I have some kind of object like a vector that I want to rotate around. I only have to worry about that one rotation. I don't have to break it into components of X, Y, and Z. So let's write that down, 1 degree of freedom. This is just theta does not need to be broken into theta X, theta Y, or theta Z components. Okay, it's just theta. We're going to see. Okay, it seems really complex. There's a lot of stuff going on, but don't worry. We're going to deal with it all. Okay, I'll let you guys finish writing that, and then we're going to talk about some properties of quaternions before we get into some of the details about it. Okay, you guys all set? Great. All right, let's talk about our properties of quaternions here. Okay, so let's call our quaternion Q. I'm going to call it S plus X times I plus Y times J plus Z times K. Scalar plus an X, Y, Z component of my vector. Okay, so this is how I'm breaking down my quaternion. Okay, so I'm going to say this is 1. I'm going to say that quaternion 1 times quaternion 2 does not equal quaternion 2 times quaternion 1. Okay. Order matters. We're going to see as we go that the order is going to matter. If I do quaternion 1 times quaternion 2 times quaternion 3, that's equal to quaternion 1, 2, 3. So I can do that. I'm not really changing the order, and I'm just kind of grouping which way I'm doing stuff. Okay, so I've got quaternion 1 plus quaternion 2 multiplied by quaternion 3. That's the same thing as if I were to say quaternion 1. So if I'm in this position here, I can factor out, right? Sorry, this should be quaternion 1 times quaternion 3, quaternion 2 times 1 times 3. This should be 2 times 3. Okay, so I'm distributing 1 and 2, quaternion 1 and 3. Okay. That'll be good. I can then factor out my 3 and then work it there. Just watch your order, right? I want to see, look, quaternion 3 happens second on each one, so it has to happen second after I add it. All right. If I do this one, quaternion 1, quaternion 2 plus quaternion 3. This is equal to, watch what's happening, quaternion 1, quaternion 2 plus quaternion 1, quaternion 3. See how I preserve the order, right? Quaternion 1, I'm multiplying that first by the addition, so the quaternion 1 comes first when I go to multiply. Remember how we said the order was important. So I'm preserving the order when I'm factoring or when I'm distributing. Say I have a scalar, right? And I want to do A times quaternion 1 plus quaternion 2. That's the same thing as A times quaternion 1, A times quaternion 2. It's more likely that I would be in this position here where I'd recognize I had a scalar that was the same. I could factor it out, add these quaternions together, and then multiply it again. So I'm only doing 1 multiplication instead of 2 multiplications. Right, so if I have A times Q1, and then I multiply by Q2, that's the same thing as multiplying the 2 quaternions together and then multiplying by a scalar. So we're not losing anything. Okay, so now the big one, and I'll put a red star around it. This is Quaternion multiplication here. This is the piece that's used in when we go to do rotations. We were multiplying quaternions together. So I would say quaternion 1 times quaternion 2 looks like this. Watch what's happened. If I say quaternion 1, I'm going to call it like this, x naught plus x bar. And then quaternion 2, I'll call y naught plus y bar. So remember, x naught is our scalar, y naught is our scalar, x bar is our vector component of quaternion 1, y bar is our vector component of quaternion 2. So when I go to multiply these two quaternions together, there's a process. I have to take into account all these pieces. I've got scalars, I've got vectors, I've got scalars and vectors. Okay, so watch what I do first. The first thing that I do is I'm going to write it like this. I'm going to say x naught plus x bar times y naught plus y bar. Okay, now when I go to multiply them together, it goes like this. I multiply, just plain old multiply the scalars together. So I'm going to say x naught times y naught. Those are just scalars. I get to subtract out the double countings, which is the dot product x dot y, right? So this is a scalar. Remember, dot product gives us a scalar. Okay, this will give us the scalar portion of our answer. I'll write that down in green. Okay, remember, when we multiply two quaternions together, we get a quaternion. Okay, so I need to have a scalar plus a vector. Okay, so now I'm going to deal with my vector parts. So now I've got those. Now I'm going to go x cross product y. So this is a cross product. Okay, x cross product y plus the scalar of x times the vector of y plus the scalar of y times the vector of x. Okay, and this whole thing is the vector portion of our answer. Okay. All right, quaternion multiplication. I'll put that in a box because that's important. Okay, we want to make sure we know that. All right. All right, so let me do a couple more things and then we'll talk about some examples. Okay. When we talk about a norm, we're talking about q squared, okay, our quaternion squared. And that's basically like, I'm going to take my scalar portion, I'm going to square it. I'm going to take my x component, I'm going to square it. I'm going to take my y component, I'm going to square it. I'm going to take my z component, and I'm going to square it. So this is kind of like a magnitude, right? Except that I'm not taking the square root because look, we're taking squared, right? But it looks like this. It's the norm. So if I say what's the norm of something, I take each component and I square it and I add it together. Okay, I'm not taking the square root, but it's, you can kind of think about it as like a magnitude-ish. That's the norm. When I want to do quaternion addition, right? I want to add two quaternions together, Q1 plus Q2. All I'm going to do, like I do with vectors, is I'm going to add the corresponding components together. Their answer will be also a quaternion. Okay, so these are all like kind of the foundational building blocks, right? We haven't even gotten into rotations yet, but we need to know how to do all this stuff, like, you know, what's quaternion addition, what's quaternion multiplication, before we can get into rotations. Okay, so let's do some examples from our example sheet, and we're going to use some of these things here so we can see how this stuff works. All right. Right. Example 1 says we're going to add the two quaternions together. P equals 3 plus I minus 2j plus k, and Q equals 2 minus I plus 2j plus 3k. So first thing, when I see these, I'm gonna write down my P is equal to 3 plus, right? This is my coefficient for I is 1 My coefficient for j is -2. My coefficient for k is 1. That's my first quaternion, my scalar plus my vector. My second quaternion, q, my scalar is 2 plus -1 is the I component, 2 is the j component, and 3 is the k coefficient, okay? So now if I'm going to add these together, p plus q, I'm just going to add the corresponding components together, okay? So when I go to do that, I'm going to add the scalars together. So I'm going to get 5 plus 1 minus 1 gives me a 0. Minus 2 plus 2 gives me a 0. 1 plus 3 gives me a 4. Okay. I can also write the p quaternion as 3, 1, minus 2, 1. My q as 2, minus 1, 2, and 3, right? Which means that my answer is going to be 5, 0, 0, 4. Okay, but remember there's a scalar and a vector component. So scalar and then the vector component, okay? Each of these is equivalent, right? But the point is that we're adding the corresponding components together, okay? What's the norm here? So let's write down q as our corresponding pieces. So I've got my scalar, right? This is -1, 2, and 3. Okay, -1 is the coefficient of the I, 2 is the coefficient of the j, and 3 is the coefficient of the k. So my q squared, my norm of q, is going to look like 2 squared plus -1 squared plus 2 squared plus 3 squared. Kind of like our magnitude, but look, we're squaring it. So this is 4 plus 1 plus 4 plus 9. 8 plus 10 is equal to 18. Okay. So far, so good. Okay, I'll do a multiplication example. I'll start it, and then we'll see how we're doing on time. Okay. All right. Example 3, we want to multiply these two quaternions together and see what we get, okay? So first thing, I'm going to write it, my p quaternion is going to look like this. My scalar plus 1 minus 2, 1. And my q quaternion is going to look like scalar plus my vector, -1, 2, and 3. Okay. All right, so now we go to multiply them together. So p times q is going to look like 3 plus 1 minus 2, 1 times 2 plus -1, 2, 3. The multiplication is the basis for your rotation. So let's, make sure that we really understand how we're going to multiply these two together. Okay, so remember, let's write down our formula for multiplying. So our formula for multiplying, so this is, we'll call it P naught plus P vector times Q naught plus Q vector. I'm going to write down my formula first so I can fill in the blanks. So the scalars minus the dot product of the vectors plus cross product of those vectors plus P naught Q plus Q naught P. Okay, we'll do these in, I'll do them in different colors so we can keep track. So I'll do my scalar portion in purple. I'll do this one in green. I'll do this one in red. And then I'll do this one in black. Just so you can see the different pieces, and we'll color code it just because I like colors. All right, so let's take it piece by piece. So we're going to do P naught Q minus the dot product with Q. Okay. P naught Q naught, sorry. So right, 3 times 2 minus the dot product of P and Q, the vectors. So this is P, this is Q here. So this is going to be 1 minus 2, oops, 1 dot with -1, 2, 3. Okay. So this is 6 minus. So let's go ahead and do the dot product. Let me make that look nicer. easier to read. -2, 1, there. All right, so now I'm going to go, I put a bracket around 1 times a -1 plus a -2 times a 2 plus a 1 times 3. So this is -1 -4 plus 3, right? So -5 plus 3 is a -2. So 6 minus a -2, 6 plus 2 equals 8. Okay, so that's our scalar portion of our multiplication. Okay. And you know what I think I'm going to do? I'm going to wait until next time. We're going to go through the this portion here. We're going to do our cross product. But I want to wait next time because we only have 5 minutes left and it's going to take me 5 minutes just to even set it up. So let's wait and then we'll do that next time. Okay, guys? Okay, I'll see you on Wednesday. Have a great day. And don't forget, we have a quiz that opens up at noon today. Okay? Bye, guys.